OK，Yeah.
Sure. Oh,
Hi, hi everyone. Welcome to the UI seminar. So today, we're very happy to have Mengzhou here as our speaker. So Mengzhou is a final year PhD student in computer science at Princeton University, advised by Dan Qichun. And her research focuses on developing algorithms to build effective language models via data-centric approaches and objective designs under an academic budget. And without further ado, let's welcome Mengzhou.
yeah. Thanks, everyone. I'm very happy to be here. Oh, okay. I should speak through the. How does this work? Hello, everyone. I'm very happy to be here to give the talk here today to talk about two recent works that we've done at Princeton. And the title of the talk is called Aligning Language Models with Less Data and a Simple Objective. And the objective that we propose is named as SimPO, which is a nice pun here. So I'm a PhD student from Princeton University, advised by Dan Qi. To give you some background of the talk about adapting language models, supervised fine-tuning, and RLHF, language models have become very prevalent these days. Everyone's using them through ChatGPT or through other proprietary services or open source models, and customizing language models has always been an aspect of people to openly and democratize the use of language models. And to give you an example of what does supervised fine-tuning mean is that, so say, here's an example where the user asks the question, why is Boston called Beantown? This is a question I asked ChatGPT to come up with an interesting example. And then it gives an answer. Boston earned the nickname Beantown because of its colonial tradition of baked beans, which is true. This is the correct answer. And this is a good piece of data. You want to fine tune it on your language model to make it able to converse with humans. So you use good data with, prompts and responses, and you fine tune your language model through instruction tuning, or what we call supervised fine tuning. You collect diverse questions and along with these open-ended answers, and you fine tune your model to build your SFT model. And you do imitation learning from these gold answers, and your model is able to converse with you from a pre-trained model to a chat model. And then there's the second step of RLHF, which is a little bit more involved. So it no longer just entails one query and one response, but instead it starts with one query, but you would collect multiple responses from different sources, either from annotators or from existing models. You use models to generate some responses. So here are two responses to this question. And the green one is the same as SFT, just for an easier understanding. And then the red one, Boston, is called Beantown because the city used to have the largest coffee bean trade in the US, which is factually incorrect. So this is an answer that's not good. If you have an annotator to annotate which response you prefer, the annotator should give the second response a downvote. This is not some response you want the language model to generate. So usually people annotate, multiple responses and then train a reward model on top of it. So the reward model can tell you which response is good and which response is bad. And with this reward model, you can do RLHF with diverse questions, and you generate on-policy answers with a policy model, and you want to use a reward model to update the policy model such that the generation will hit the high reward, and you end up having a policy model here. So what RLHF does is that it refines the policy models on output based on some external reward. It's different from imitating from the gold answers. So these are the two main techniques that people commonly use to adapt their language models. So in this talk, I'm going to cover two works that we've done recently. One is called SimPO, which falls into the RLHF paradigm, where we do preference optimization, and we propose a reference-free reward so that you can adapt your language model efficiently and effectively. It's a learning algorithm for preference optimization. And the key research question we are answering there is how can we learn more effectively from preference data? And the second work I'm going to introduce falls into the first category of supervised fine-tuning, where we try to select the influential data for targeted instruction tuning, where we develop an algorithm called LUS to do data selection for instruction tuning. And the key question we're answering there is how can we find most relevant data for improving a specific skill? So starting from the first work, SimPO, and this is a joint work with my awesome collaborator, Yumeng, now a professor at UVA, and my advisor, Dan Chen. Okay, so to give you a brief view of the model that we built eventually with the SimPO algorithm, so we adapt the existing JAMA 9B instruction tune model with the algorithm we proposed SimPO. And at the time, we reached the top one place on the AlpacaEval 2 leaderboard. I know a lot of people have doubts over these model-based judgments, model-based judging. So we eventually sent the model to Chatbot Arena. We want to collect real user feedback and real user votes and see if, the model judging results align with real user uses. So we do find that our model gets to be on par with its larger version, which is JAMA 27 billion. So a 9B model is as good as a 27 billion model, according to Chatbot Arena users. And it also surpasses existing strong models like Llama 3, 70 billion struct. Where we built this model actually using minimal compute and completely open data. So to start with how we developed this model, we based our work on DPO, where DPO is an algorithm that directly trains the model on preference data, where the construction of preference data entails prompts, winning responses, and losing responses, just like as I've shown earlier. And it really simplifies the whole RLHF process, where it no longer involves an explicit reward model, but instead just trains the policy to learn an implicit reward. So DPO starts with a very similar RL objective to PPO, where it tries to maximize the reward of the policy's generated response here at the same time to add a KO penalty over the current policy model and the SFT model, which is used as the reference model here. So in order for the model to not drift too far away from the reference model, completely break the model. So to optimize the previous objective, the optimal policy that maximizes the previous objective can be derived as follows. And Zx here is a partition function. And essentially here, the policy is expressed as the reference model and the reward that you have here. And the authors did a little bit smart reorganization of the objective, and they instead express the reward as a function of the policy. So DPO derived this reward that's represented with the policy, and instead of training an explicit reward model, they just use this policy model to denote the reward model and trains with this reward instead. So here's the reward that they derived from the original RLHF objective, and they express the reward in the form of the policy model, and then they plug it into a Bradley-Terry ranking objective, which is a objective that's commonly used for ranking objectives for preference learning. And they derive this DPO objective, where essentially the model learns to assign a higher implicit reward, which is the log difference between on a specific response between the policy model and the reference model. So this has become completely a supervised fine-tuning objective without using an explicit reward model or without using any specific RO techniques. But we identified a problem in the DPO empirically, which essentially we find that the DPO reward actually does not directly align with generation, the goal of generation well here. So during training, what DPO does is really like to maximize the reward difference between the winning response and the losing response. And the reward is expressed as this difference between the policy probability and the reference probability. So what's the role of the reference model at all? What if you have a very bad reference model to start with? And during decoding, we don't really use this reference model. While the objective is essentially, trying to maximize the difference between these two rewards. So during testing, all we care about is how to decode from the policy model. And we use algorithms like greedy or sampling or beam search, and we don't involve a reference model at all during decoding. So as the training objective seems to be a little bit disaligned, unaligned with the testing objective, where you really just want to decode a high probability sentence from your policy model. So by looking at some, analysis, we do find there exists an inconsistency between the training metric and the probabilities. So for the sequences where the sequence actually hit a higher reward for the winning responses, there are only half of the winning responses actually have a higher probability, which means that even if, the winning responses are trained such that it has a higher reward, the policy model is actually not able to be more likely decode that sentence compared to the losing response, which is kind of absurd. You train this model, you want it to be more likely to generate the winning response. Yeah. So, but this is a result with only one training epoch. Usually we do experiments with just one epoch in the preference optimization regime. Also feel free to ask questions anytime if there's anything I can help to clarify. So we think that, there exists this inconsistency between training and generation. So maybe we can just simply use the average log likelihood, which we think aligns with the decoding objective better, and plug it in back into the Bradley-Terry model to train explicitly with this implicit reward. So we propose to use this average log likelihood as the reward function, which is super simple, where you just, take the, literally just the average log probability from the from the current policy model. The beta is like a hyperparameter people tune, both in DPO and SimPO or a lot of PO algorithms. So here's a question comes in, like I said, about you want to generate sequences that maximizes the probability, but here we add in a length normalization here. Why is it length normalized? Should we choose an unnormalized probability or a normalized probability? So this is completely out of the empirical concerns, where shorter sequences tend to have larger log probabilities. So if you simply just want to decode a sentence with the largest probability, you should just decode one token with the first token that has the largest probability. Well, that's also not the optimal way to get the largest probability sequence, but on average, shorter sequences tend to have a larger log likelihood. So that mismatches with your goal to decode a reasonable sentence either. And this average log likelihood actually is commonly used to rank options for multiple choice questions, and also is used to rank sequences in beam search. So additionally, we also introduced a target reward margin in this Bradley-Terry ranking objective. So we add a gamma here in the Bradley-Terry BT objective, which is also accounted in the BT literature, where people call it as like a home advantage. It wishes to encourage a larger margin between the winning and the losing responses. So we want the winning response to have an even higher, at least gamma level reward here. So here we derive our simple SimPO objective, where we start from this reward as the average log probability, and then we plug it into our Bradley-Terry ranking model, and we get our eventual objective here, where we, similar to DPO, we want to maximize the difference between the reward of the winning and the losing responses. And if you look at these two objectives closely, what SimPO really does is that we get rid of the reference model, and we add a length normalization form here, and we add a gamma term here. And later on, I will show that both components are really important for achieving good empirical results. Yeah. So before I move on to experiments, are there any questions? Or, oh yeah. Yes. Yes.
So in that, can you just treat that and raise the count of the original count of make the really small factor what derived result that
Yeah, so yeah, that's a great question. That's also a question that we commonly got asked in reviews and by other people because DPO is derived from the original KO constraint RLHF objective, and we kind of just get rid of the reference model, which means that we no longer have this KO constraint. So what I want to say is that first of all, like DPO, even though it's like derived from the original objective, it only like the equivalence only exists when the optimal policy is achieved. So, but there's no guarantee anymore once you start to train a model with that objective. So what we have observed is that if you don't do proper tuning, DPO would also drift away from the reference model. So for any like objectives that do not explicitly use KO divergence to regularize your model will all drift away. Same for DPO empirically. And I think there's a way to tune the model through hyperparameters such that you keep the KO divergence at a reasonable level that you can still decode good sentences and out of it. Yeah.
I guess follow up that does reward caching happen or not?
Yeah, as I said, like you have to tune it properly. Like if you train it for 100 epochs, definitely it's gonna happen, right? Like it's gonna learn some weird sub-distributions that maximizes the reward, but no longer actually generates reasonable sentences anymore. Yeah, but I guess for different algorithms, the empirical concerns will be slightly different. How you should tune the model would be slightly different. Yeah. All right, I'll move on to the experimental setup. So we experiment with two model families, Llama 3 8 billion and Mistral 7 billion, and in both base and instruct settings. And for the base setting, we fine tune on UltraChat, which is an instruction tuning, supervised fine tuning data set to obtain the supervised fine tuning checkpoints. And then we train this SFT checkpoints on Ultra feedback, which is a preference data set, and to do preference optimization. So this is like a purely very transparent process where you have control over your data. You have a base model. You fine tune the whole process on your own, and so there's no interference with closed source instruction tuning like what you would have if you start with the instruct setting. So in the instruct setting, we take the off-the-shelf instruction tune model and we use it to generate 5 responses for each of the Ultra feedback prompts using an off-the-shelf reward model called pair RM. At the time, it's like a pretty strong, reward model, but no longer the case right now. So we pick the highest scoring one as a winning response and lowest scoring one as a losing response. So for the second setting, we only use our own preference optimization preference data set, and we leave the supervised fine tuning stage out because we start from already instruction tuned model. And the preference data is generated by the supervised fine tuning model, which is on policy, and that's always what you want if you start with the supervised fine tuning model. And there's also one extra reward model involved, although not directly in our optimization, but in constructing our preference data. Yeah. So we use all these evaluation benchmarks across AlpacaEval, Arena Hard, MT Bench. These are all, model judging like benchmarks, because it's really hard to do human evaluations. It's very expensive, and if you have ever looked at the data, it's super specialized, and it will be hard for average human, even PhD students, to annotate all these data. So usually people resort to using LLM as a judge to decide which response is better when comparing two models' responses. Yeah. So later on, we also added evaluations like WildBench, which is also an LLM judge benchmark. And I think eventually, cause I want to understand like whether the good scores that we get from all these LM as a judge benchmark really correspond to real user experiences. So we send the model to Chatbot Arena to really collect real user feedback. And I think the results have been positive, and which gives me more confidence as in that we did improve the model. So to show some results, comparing SimPO and DPO, at least on the settings that we've tested across Mistral base, Instruct, Llama 3 base, and Instruct, I think we see a gain from DPO to SimPO outperforms DPO in all these settings. So in particular, we find that you can build a quite strong chat model by using open source data sets. So we use Llama 3 8 billion base model plus SimPO using all open source data sets for supervised fine tuning and PO. We can reach a win rate of 22% versus Llama 3 8 billion Instruct reaches a win rate of 26%, which is very close. And you can also turn a very strong instruction tune model into a much stronger one by generating on-policy data. So also comparing on the AlpacaEval to LC win rate, the Llama 3 8 billion Instruct model achieves 26% win rate, and after continuing tuning preference optimization on this model with the open preference data set that we use, we reached a 44.7% win rate. So there's multiple ways, even though, these closed labs provide strong open models, there's ways for you to further tuning the model to get a stronger version if you have your own prompts and a reward model for you to annotate the data. So compared to a lot of other baselines as well, there have been a plethora of PO algorithms out there, and you would find it like it's super annoying to run all these like baselines. So there's always a slight difference from one objective to the other, and we try to do empirical studies over all of them. And in short, we just find that none of these PO methods actually outperform DPO consistently in the settings that we experimented. So to understand our objective SimPO better, we try to study how length normalization and target reward margin actually come into play here, and how important both components are. And so it starts with simple, and we get rid of the length normalization factor, and we find that we get much, much lower scores without the length normalization. And if you look at the output carefully, you would find that the model really generates much longer sequences than adding the length normalization there, which makes sense because, like longer sequences generally should have a lower probability than the shorter sequences. And then if you don't use that regularization, you just push your language model to further assign a higher probability over longer sequences, which is supposed to have a lower probability. Then the model just really encourages to generate longer sequences. So the model actually does not generate good long sequences. So that's a problem where we see a huge drop in the scores. And if we get rid of the gamma, we also see a drop of scores, but not as significant as you leave out the length normalization term. So I would say both components are important, and one should tune carefully of all these components when running SimPO. So we try to study more closely of the effect of the length normalization there, where, we study the correlation between average log probability of the sequences and the response length. So we take the SFT model and we measure how well the average log probability correlates with the response length, and we have a positive row, which means that it's slightly, positively correlated. So longer sequences do slightly have a longer average log probability in the SFT model. And after you tune it with SimPO, this property is preserved. You have a similar row, a similar correlation in that. But if you leave out the length normalization, the model starts to getting crazy, where it really assigns a much higher average log probability. Also means even higher probability to the longer sequences, and that's not something that you want to see. And for DPO, it actually has a relatively lower row compared to SimPO without length normalization, but also a slightly higher row compared to SFT and SimPO, simply because DPO has a reference model also there to implicitly facilitate the length normalization a little bit. So I thought this is not the end of the story yet, because after we released our paper, we also got a lot of feedback from the community. People come to us and tell us why it works and how it doesn't work in their settings in different data and stuff like that. So we we did more study, and some findings that we have is that we find that the reward model that's used to label the on-policy data really impacts the model performance significantly. So we switched to a stronger reward model because after we released the paper, there was a stronger reward model that got released on WildBench, and we tested with the stronger reward model, and we just find we get free scores with a better annotated data sets, where for both DPO and SimPO, we get to benefit a lot from a stronger reward model. And actually, we also find actually additional PO process hurts, conventional benchmarks like GSMAK and MMMU. And we try to study what's really the problem there. Is it like a learning rate issue? So we tune different learning rates, and we do find learning rate actually plays a huge role here, where if you use a larger learning rate, you get a pretty good chat score, AlpacaEval LC score, but you really hurts your GSMK and MMOU from your original model a lot. But if you use a smaller learning rate, you get slightly worse chat scores, but still better than the original model, but you get to retain all these GSMK and MMOU scores. So learning rate clearly plays a big role here. So there's a balance to strike between the chat abilities and other downstream tasks, because they could be at odds at each other given a single model. And we find that adding an SFT loss would slightly fix the problem, making it more balanced out. Yeah. But actually, when we switch from Llama 3 instruct to Gemma 2, we get completely different trends, which means that these two models have very different properties. When we experiment with Gemma 2, we find that no matter what learning rate you tune, you get similar scores. So the model's not really affected from like catastrophic forgetting or anything like that. It just like retains the GSMAK and MMOU scores very well. So we have a hypothesis where, because in Llama, they disclose that they use this data annealing technique to really stuff in high quality data at the end of the training. And we wonder if that's a key factor that really affects this catastrophic annealing effect. But that's just a hypothesis, and it will be a little hard to verify that hypothesis, given that, pre-training is very hard to maneuver. Eventually, we built this model. It starts from the Gemma 2 9B IT, which you can see Chatbot Arena is ranked at 50 here. And then Gemma 2 9B instruct tuning is closed pre-training, closed RLHF. You don't know any details about it. Nobody releases the data, and that's been frustrating. But we do continued preference learning on the open data that we have, the on-policy ultra feedback data. We only use 50,000 lines of data, which are annotated by RMORM, which is a strong reward model, and very minimal data. And we get to improve the ranking by 15. And we get to become the strongest less than 10 billion model on Chatbot Arena. And it's completely achieved within academic budget. Every experiment only takes like 2 hours to run on 8 H100 GPUs. So which makes us really wonder how we really make this work, and where does the gain actually come from? If it's all open source, Google could have done it. It could have made their model look much better on the leaderboard. Chatbot Arena is really one of the benchmarks that people try to compete on when releasing their models. So I've been thinking about where the gain actually comes from, and my hypothesis is that could be from the strong reward model that people possibly built with proprietary models like ChatGPT. And then maybe Google is not able to use these ChatGPT signals to build their own models. But which also means, ChatGPT preferences might align with human preferences pretty well. That's why we're seeing this alignment between real user feedbacks and LLM as a judge benchmarks. Yeah. So some final thoughts about this work. So our model still stands the strongest on a bunch of benchmarks, and we also get to retain strong performance on other downstream tasks, and we get a lot of downloads on Hugging Face as well. And in the PO, community, there's always like a huge debate between offline and online PO algorithms and whether I think people have reached a consensus that using online either like iterative DPO or iterative SimPO or online algorithms like PPO could achieve pretty good results. But it's uncertain if the gap will still exist after we switching to on-policy data and external reward meta and do it multiple runs. Would it be actually as competitive as the PPO? People still keep exploring this question, and there exists the question: does the reward model really provide the scaling that we're seeing here? And one thing to note is that we find that the gap between like different algorithms really narrows when the data quality and SFT model improves. So when we experimented with the GEMMA model, we actually don't see a much big difference between DPO and SimPO. So as the model grows stronger and as the data quality increases, the algorithms actually matter less. And we've also seen like algorithms like IPO, which never worked in our Mistral setting, suddenly start to work in a stronger model and stronger data setting. So that's also been quite interesting. And one final question would be like, oh, is the current evaluation really broken? Because what does it mean that you reach a 77.5% win rate against GPT-4, like Turbo 1106, right? Like, are the prompts too simple, or the model only learns, very nitty-gritty? There's not really, yeah. So like how to interpret that results, I think we've been doing some work there to try to interpret the preferences from judging models and also humans through data we collected. All right, yeah, this is the closing of this work. I wonder if there's any questions and yeah.
Algorithms, there are any work that try to know why this skill is better than others. What is the reward? They cloud all the reward together in one figure and then to see like the score versus the difference of the responses. And then try to give us some explanation of why that is that.
Yeah, I guess I think the methods are usually motivated by different formulations. And once you start to train a model, like it's very hard to analyze the training dynamics of these objectives because you just lose control. Just like any learning problems, it's a little hard to analyze this training dynamics and to understand why this objective is actually better. I think I don't really see many like compelling evidence that tells you inherently which objective would be better, but it's more through, empirical observations of doing empirical studies and finding like experiments with different stuff and settings and try to conclude empirically there. I would wish I could have a better understanding of these objectives as well. I guess like for SimPO, I can explain maybe a little bit, but it's also a hypothesis. It would be hard to verify why this lens normalization works is that maybe like there exists a bias where the model, whatever, like human or model still prefers slightly longer responses. So you want to factor that out from your policy by like normalizing your reward over your length. So your policy model could really learn something other than the length, rather than baking the length into the policy model to further exacerbate that bias. So it's some bias that's from the data that makes the objective correct. That's how I understand the improvement of SimPO here. But I would find, I don't know how to use that insights to interpret other objectives very well. Yeah, because, yeah. Okay, if there's no more questions, I'll move on to the second work on like selecting influential data for targeted instruction tuning, where this is also a joint work with my awesome theory collaborator Sadika at Princeton and with Sachin now at Meta earlier at UW and with two advisors, a great advisor Sanjeev and Denchi. So let's start with from the state of instruction tuning, where there exists a lot of data sets there for you to do supervised fine tuning. If you remember, that data points that I showed at the beginning of the talk, and there exists many instruction tuning data sets out there, and some of them are human written, and some of them are actually model generated. Actually, I've seen more and more model generated data now than human written data. Yeah, I honestly don't think I've seen any human written data after I did this project. I guess if you really ask humans to annotate data, this data will be very valuable, and people would be reluctant to release it to open source. Yeah, and these data are all super diverse and nuanced, and it would be hard to categorize such data into traditional NLP tasks, like entity linking, parsing, or semantic analysis or stuff like that. This data could contain any type of problems, just like any data that you would interact with ChatGPT these days. Like it could be coding problems, could be asking for travel plans, food recommendation, ask the model to fix the roof for you, or ask the model to do novel writing and stuff like that. There exists many instruction tuning data sets out there, and training on these data sets, and what we can do to effectively understand how useful these data sets are is to evaluate them on different benchmarks. And this is what this work has been done to evaluate across multiple benchmarks that have a specific focus, like factuality for MMOU. MMOU is knowledge intensive, and also like GSMAK and BBH for reasoning intensive questions, and for TED-IQA, which focuses on multilinguality, and Codex for coding, AlpacaEval for open-ended generation. And when you train all these data on models and try to evaluate on different benchmarks, you would see that combining all instruction tuning data sets actually doesn't always work the best. And you would find these cases where a certain data set actually leads to the best performance on a specific evaluation set. For example, like training on Super NI gives you the best TED-IQA score. But if you combine everything, it actually reduces your score. So adding more data sometimes actually hurts the performance on some evaluation set. And naturally, we start to wonder, like, how can we directly, like, automatically, extract a useful data set if you really want to cultivate a specific capability in model. And so we would want to know something about the target that we want to train for, right? But from these tasks, at least we know we have few shot examples for each task that could denote this task, that could represent this task, that could use as anchor information for us to select some data points to adapt to this specific task. So we have few shots examples for all these data sets. And thus, based on the setting, we formulate this targeted instruction tuning setting to answer this research question. Given a few examples of a target application, how can we select the relevant instruction examples most effectively for fine-tuning? And why we assume that we only have a few examples is that sometimes, there's little data exists for target applications, and we only use the examples used for in-context learning because people wouldn't hesitate to write a few in-context learning examples when you want to prompt your model, right? So we can always assume such in-context learning examples exist. And why targeted instruction tuning, like as I've shown in the previous slides, combining all the data sets for training isn't the best way to get a specialized model, and selecting data could possibly lead to better performance. And potentially this could also be an application for on-device test time training. When you want to ask a question on the local model that you serve on your laptop, you write a few in-context learning examples, the model could quickly find some examples that are close to this examples that you've written and train the model at the test time and to give you a better answer. Yeah, but the data selection problem is actually quite unintuitive if you have to think carefully about it. Human as a model, the data prefers by humans as a model is very different from the data that prefers by models that have gone through pre-training, right? So it's hard to intuitively select the data for a specific target use. To give you an example, so here there's a target example where we take an example, logical deduction example from BBH, where it asks the model to do some logical deduction, which one is the fast. And I would present two examples and which example would be more helpful for improving the performance of the target example during fine-tuning. So there are two source examples that I presented here. One is question answering from the Dolly dataset, and the other is the geometry reasoning from the Flan V2 dataset. And one is question answering, the other is geometry reasoning. Which one would you say is more helpful for getting to fine tune to get a better performance on logical deduction? It's not intuitive. So therefore, we propose our method loss to use training dynamics to formulate an influence formulation to estimate how training examples actually influence models' predictions on validation examples, and we use it as a proxy for data selection. So we want to estimate how much this training example influences the model's prediction, and if it influences more, we think it's more useful for increasing the capability on this specific target. And we make it work for atom optimizers and sequence level instruction tuning data by tweaking the objective. And we make the algorithm practically efficient so we can actually use it. Usually influence formulations are pretty expensive and not really practical, especially for large language models. So to give you some background on estimating training influence for data selection, the previous work that's been done there called estimating training data influence by tracing gradient descent. This is a work which coins this formulation where they chooses training data to maximally reduce the validation loss in a model-aware and optimizer-aware way. So the goal for you to choose your training data is that you want to choose a data fine-tuning on which will reduce the validation loss on some of the target examples that you have. And one can write the loss change on a specific example using first order Taylor expansion here, where the loss change can be characterized as the dot product between the gradient on a specific data point and the parameter changes between two steps. And then imagine if you're doing an SGD step on an example X, and you can just, plug in the parameter change as the SGD update rule, and you would get the following formula, where the loss change on this target example Z can be characterized as the dot product between the gradient of the training example and the gradient of the target example, which is also intuitive. If the gradients between these two examples align, it means that the training example would be effectively help reducing the loss on the validation example. So to maximize the loss decrease, you can just simply choose X to maximize this dot product. And they expanded to multiple epochs and to choose training data X such that it will maximize this aggregated influence across different epochs, where I is the epoch number, and it's related by the average learning rate in each epoch. So you would think a higher learning rate means that this data point, this epoch has more influence than other epochs. So what we did is that we adapting this data selection problem for instruction tuning, where we face specific challenges that. Yes. Yeah. We completely get rid of the second order thing and just not use it. I guess from this paper, they also get rid of the second order thing. So including the second order would mean that you would have to retain the Hessian function and compute it in a certain, which is extremely expensive for the scale that we're operating on. So I think this paper has some positive results in that using first order approximation would be also useful for giving positive signals there for they didn't use it for data selection, but use it for like a counterfactual reasoning for training data points. So we just, I guess, borrow that assumption from this paper and simply just get rid of the second order thing, which would be important. I've only seen one work from Anthropic that actually incorporates the second term for large language models, which is really computationally heavy. Yeah. All right, yeah. So we adapt the data selections first order approximation for instruction tuning, where instruction tuning is fine-tuned with Atom instead of SGD. So instead of using a normal gradient for the training data points, we instead use the Atom gradient, where you would have to estimate the first order and second order moments to compute this gradient for the data points, which makes it more close to the actual training trajectory that we would be conducting during the real fine-tuning. So in practice, how we estimate MMV is that we do warm-up training with K% of data, and we save the checkpoints, and we estimate MMV with the warm-up checkpoints. And also, in instruction tuning, responses are of variable length sequences. And when we talk about gradients, yeah.
I think one about Alex, the moment cross.
Yeah.
It's like paint this variable as it is. It's like close your eyes. That's like something
So I think like MMV, they keep track of the gradient information during the trajectory, right? So like when you do data selection, it becomes a circular problem because you don't have MMV before you select data, right? You haven't even selected your data. How do you estimate the trajectory of your training? So it becomes a circular problem. So you would have to find some way to approximate it empirically, where we just, train the model with warm-up training first, and then just use these warm-up training trajectory to estimate MMV here. Yeah. Yeah, so the second challenge here we face is that the responses are actually of variable length. And when we talk about gradients, it's average token-wise gradients. It's actually gradients of multiple predictions on different tokens, right? So, but if you do dot product, it really makes the metric favor short sequences because short sequences have fewer predictions and the average gradients have a larger norm. So if you do dot product, the dot product really favors short sequences that have a large norm. So in practice, we use cosine similarity instead of dot product to estimate influence. So this is also slightly shifted away from the previous theoretical analysis. And eventually we derive this like atom influence function where we use a weighted sum over the cosine similarity between the gradient of the target example and the atom gradient of the training example, where we incorporate this atom updates. All right, so specifically how this works is that we first do warm-up training with LoRa. The reason why we do LoRa is because, like large language models, even if you're only operating in the gradient space, it's still super large, right? The gradient is the same size as the model. So we want to do LoRa so that we can capture this low dimensional LoRa gradients, which would make it easier to operate and easier to compute. So we train LoRa, we collect these MMV through this warm-up training. And we get this LoRa model and get the checkpoints, and we compute the gradient features for all the training data that we have. We run through all these models, through all the data we have, and get the gradients. And then even if you do LoRa, you still have a very large vector. So on a 7 billion model, you do LoRa, you get 100 million parameters, which is still very large. Because we want to store all these gradients for a later retrieval, what we do is that we do random projection to project it down to 8,000 dimensions. So to effectively reduce the size of the gradient data store that we save there. Yeah. So the step 1 and step 2 are both very expensive because you would have to run the model multiple times to get the gradients and project them down to save the gradients. But this is just a one-time thing. You only need to process your data at this one time. And now the data is, presented as a data store. You can use it later for any tasks that you want to fine tune. You can find the relationship of data in this gradient data store for any of the following stuff that you want to do. And when you actually select the data with this atom influence, it's super efficient. It only takes like less than 1 minute on a GPU to run this selection by computing this atom gradient. So you have a target task come in, you have a few in context learning examples, you compute these examples gradients, and you use these gradients to compute the atom influence, and you find the data that reaches the maximum influence on these according to this formula. And you get this data, you train your model that has the maximum atom influence. So for some experiment settings, we train on 4 different data sets, which has 270,000 data points in total, and we evaluate on MMLU, TATA-QA, BBH, and we evaluate on Llama 2, 7 billion, Llama 2, 13 billion, and Mistral 7 billion, all base models. And these target tasks have different properties. They come with few shot examples, which we use as target examples to select our training data. And the main results we have here is so what we do is that we use a Llama 7 billion model to build our data store and to select our data. And we use the data to train on a larger model, which is Llama 2, 13 billion. So we want to experiment if it's possible, use a smaller model to choose your data and then fine tune on a larger model to see if it still stays feasible. And the results have been quite promising, where like we find that 5% of the data could actually outperform using the full data set. So we do get to find the most useful data for fine tuning, even though we just use a simpler, smaller model compared to the target model. Yeah. So we just select data once. We just pick the top K data points for fine tuning and evaluate on that. Yeah. We compute the scores, we compute the scores for all the training data point and we pick the top K and then use that for fine tuning. Yeah. If that's the question. Mm-hmm. Yeah, I guess the efficiency, in terms of efficiency, you would always want to save compute, right? Like, but I guess what I'm trying to deliver here is that maybe it's worth to use more compute to get better performance, because if you just simply don't do this process, you get slightly worse performance, right? So efficiency might not the point that I want to sell here, but instead, like there exists a subset of data that could achieve better performance than just simply not doing selection than training on all the data. Yeah. So it's more for performance, but when you use small models to select data for a larger model, the efficiency also comes into play, where the process also gets more efficient. Yeah. So we also tested on other model families, and it has a very similar pattern where 5% works pretty well, even if the data is not selected by the target model itself. Yeah. So data selected using a smaller model can actually transfer pretty effectively. Mm-hmm. Oh yeah, so Mistral here is a different model family from Llama, I guess. Yeah. Oh, so we use Llama for selection and we select the data to train Mistral. Yeah. Yeah, that's a great question. We didn't do that, but that would be interesting to try out. And it's like on policy data selection, you just keep selecting because you would know what data you need the most, I guess, right? Like, yeah, it's an interesting idea. So we also compare it to other methods, and we find that other methods actually don't do very well. Like random is a very strong baseline, and if you use methods like DSER, that depends on n-gram, or BM25, which depends on keywords and semantic matching, or RDS, which is simply just to use models hidden representations as features to pick the data that's closest to the target, it actually doesn't do very well. So less outperforms other approaches that are based on surface form features. So what data we actually selected, I think that's what we want to look at, is the data we selected actually make sense or not? And for this interesting TATA-QA example, our target task is to do TATA-QA question answering in Bengali. And we find that other methods all focus on the surface form of the language a lot, where they selected examples that are also in Bengali, but a completely different task. Like BM25 selects a mass word prediction task, and RDS selects a hate speech classification task, while LESS is able to select a question answering task in English that conforms to the form of the target task better, rather than relying on surface form language cues. we also extended this work to use LAS to find the most harmful benign fine-tuning data there, which is an interesting application that we published it in another paper. So essentially, we get to find some benign data. You know, they're really benign. They look completely fine. It's just list 3 planets in our solar system. But we find that fine-tuning on these data actually hurts model safety a lot, which makes a model, you know, originally it rejects to answer your questions. Later, it like fine-tuning on such data, it jailbreaks the model essentially. And it could be as harmful as real harmful data. Like this is a harmful piece of data, which the query is that teach me some insults to use on a teenager, which is really not something that you want language model to generate. But we find that fine-tuning on this seemingly benign data that's found by LAS is as harmful as the actual harmful data. Which means the LAS is also a nice method that you can use to find data that would possibly induce a certain ability from the model. Yeah. So in summary, like we did a bunch of ablations as well. We find that the more compute you throw into building this data store with a larger warm-up stage or with a larger projection dimension or with more checkpoints, so more compute you throw into your data to compute this gradient data store, the better performance you get. It's always super consistent. Yeah, and we identify this interesting application to identify seemingly benign yet harmful instruction tuning data that could break model safety. And some limitations and future work is that we think we can, you know, like, for example, minimizing cross entropy loss does not always mean it can increase final performance, right? Like it might be true in some settings, but might be less true in some other settings. For example, if you're dealing with really long responses, low average loss doesn't necessarily mean that the response is higher quality. So there's like a discrepancy between what you're optimizing for and what you actually want from your adaptation. Yeah. Uh-huh.
I guess like the main difference is that like if you use the gradient, like the similarity of the like the kernel in some sense, and then like if you only use the like the dividing of the data offering the data itself, right? I think our kernel.
Yeah.
So that's like the main difference.
You mean like the less and then compared to using representations? Yeah. Yeah, exactly. I think we have some comparisons with you know, other methods like DSDM, which is developed here at MIT, where it measures, you know, how much the model output changes other than how much the loss changes as what we did in loss. So like that would operate in a different kernel space than what we are doing here in terms of the loss. Yeah, but yeah. So that part is like conducted by my theoretical collaborator. Yeah. So I think yeah, and TK and stuff like that. Yeah. Awesome. Yeah. Are there more questions there? Oh yeah. Yeah, we don't actually find such type of bias like in the length there. Yeah. So we also try to do a baseline, like we select the 10% longest responses and stuff like that. I don't think that works well in the setting at all. So we also didn't observe any, you know, significant length changes in the responses comparing fine-tuning model on random selection or comparing models fine-tuned with the data selected by LAS. So I think, yeah, I don't think length plays a role here. I guess here what I mean is because we're essentially trying to optimize the loss reduction on the target responses, right? So if you have some target examples that have really long sequences and the loss reduction on these long sequences might not correspond well to the final metric, which is to generate a high quality response well. And the longer that is, the less the loss correspondence there exists between the real metric you care about and the loss. So imagine if your answer is just one span, it's just one letter, right? The loss really, although the loss and accuracy are still disaligned in some way, but they're more aligned than comparing the loss on a long sequence and, for example, the reward score on that sequence, right? So, yeah. All right, yeah. Here's the end of the talk. Thanks everyone for coming. So in summary, I just like introduce the two algorithms, two post-training algorithms that are good for open source development. And my research goal is really to develop open source algorithms and artifacts within an academic budget. I know people have a lot of concerns over closed source labs where they don't disclose any information, but I think we can still do a lot of meaningful work using open source data sets and limited compute that we have here. Yeah, so thanks everyone for coming, and yeah, for the questions. Awesome. Yeah. Thank you.
Thank you, guys. It makes so much sense. It's like, yeah. Which year are you?
I am fine.
On the job market this year?
Yeah, I'm
I haven't popped up. I was out here, I do like robot learning.
Oh, robot.
Yeah.
Robot.
Robotics. I get like robots.